Hi everyone. Today, our group will present assignment 1 for the course Programming for Artificial Intelligence and Data Science. The topic is exploratory data analysis across multiple data modalities. I'm Hồ Minh Huy, and this presentation was done by our 4 team members: Nguyễn Thế Hoàng, Ngô Trần Đình Duy, Nguyễn Việt Nam, and me. Here's the outline for today. We will start with a brief introduction of our team and objectives, then walk through EDA results for 4 datasets, 1 tabular, 1 text, 1 image, and 1 multimodal. We'll finish with a comparative summary and lesson learned. Our team consists of 4 members, as shown here, with Thế Hoàng as the group leader. Our objective was to perform comprehensive exploratory data analysis on 4 data modalities: tabular data using the AddClick dataset with 1000 records, text data using SWAT 1.1 with roughly 98,000 question-answer pairs, image data using SVHN, the Street View House Numbers dataset with about 99,000 images, and finally multimodal data using Flickr, which contains 40,000 image caption pairs. The GitHub link is shown at the bottom. Here's a quick overview of all 4 datasets and their sources. AddClick dataset from Kaggle, SWAT 1.1 from Hugging Face, SVHN from Stanford, and Flickr from Kaggle. For our tooling, we use Python 3.13 as the base environment, with standard data science libraries including Pandas, NumPy, Matplotlib, and Seaborn for general analysis and visualization. We also use other tools for text and image processing as shown here. Now, let's look at the tabular dataset. The AddClick dataset has 1000 records and 9 input features, plus 1 binary target column, whether a user clicked on an advertisement or not. Features break down into 5 numerical and 4 categorical variables. Importantly, the dataset has 0 missing values and 0 duplicates, which means no cleaning was needed at this stage. The target variable is perfectly balanced, exactly 500 samples for no-click and 500 for click, giving a 50-50 split. This is ideal for binary classification and means we won't need any resampling techniques to handle class imbalance. Looking at the numerical feature distributions, we can see all 4 key features: daily time spent on site, age, area income, and daily internet usage follow roughly bell-shaped distribution with low skew values, mostly under 0.65 in absolute terms. The negative curtices values indicate relatively flat distribution without heavy tails. Both mean and median are close together for each feature, confirming no severe outlier distortion. This tells us the numerical features are well behaved and mostly ready for modeling with minimal transformation. The correlation matrix reveals some clear and important relationships with the target variable. The strongest predictors are daily internet usage with a correlation of negative 0.79 and daily time spent on site at negative 0.75. This means users who spend more time online generally click less on ads, which makes intuitive sense. Age has a positive correlation of 0.49, suggesting older users are more likely to leak. Area income is moderately negative at negative 0.48. Notably, the gender feature has essentially no predictive power, with a correlation of only negative 0.04. This is a feature that could safely be dropped. for outliers. Only 9 outliers were detected in area income using the IQR method. The other features had no outliers at all, so the dataset is remarkably clean. The box plots comparing feature values by click outcome clearly show separated distribution, especially for daily time on site, internet usage, and area income, which aligns with the high correlation values we just saw. The pair plot now further confirms that click and non-click user form visually distinct cluster in the feature space, particularly along the internet usage and time on site dimension. This is a promising sign for downstream classification. The features have genuine discriminative power. We also analyze temporal patterns using the timestamp column, breaking click rate down by hour of day, month, and day of week. The charts show that click rate remains relatively stable across all time dimensions. No significant peak hours or seasonal effects were detected. In summary, the key findings for the tabular dataset are perfectly balanced classes, internet usage as the strongest single predictor, and no temporal effect on click behavior. For preprocessing, we recommend dropping the add topic line and CD columns as they are too high cardinality to use directly, extracting time features from the timestamp, and standardizing the numerical features before modeling. For the image modality, we use SVHN, Street View House Numbers, a real-world digit recognition dataset. It has 73,000 training images and 96,000 test images, totaling 99,000 images. All images are 32 by 32 pixels in RGB format across 10 digit classes from 0 to 9. The dataset has 0 corrupted images and 100 data completeness, which is excellent. However, there's a notable class imbalance. Digit 1 has approximately 18,900 samples, while digit 9 only has around 6,200, a roughly 2-to-1 ratio. This imbalance will need to be addressed in modeling, for example through class weighting or oversampling. Analyzing the pixel statistic across RGB channels, the normalized mean values are roughly 0.44, G roughly 0.45, and B roughly 0.47, with blue slightly higher, indicating a mild cool bias in the dataset overall. Standard deviation is approximately 0.2 uniformly across all 3 channels, suggesting consistent contrast across images. Data quality check confirmed 0 corrupted images, 0 missing labels, and 100% dimension validity. All images are consistently 32 by 32 pixels. In summary, SVHN provides 99,000 real-world digit images at a consistent resolution, making it well suited for CNN-based training. The primary concern is the 3-time class imbalance between digits. For preprocessing, we recommend normalizing pixel values to the 0 to 1 range, or applying channel-wide standardization, and applying data augmentation techniques to help the model generalize, especially for underrepresented digit classes. For the multi-model section, we use Flickr Rake, which contains 8,000 unique images, each paired with 5 crowdsourced captions, giving 40,000 total image caption pairs. Modality completeness is essentially 100%, no unpaired images or missing captions. Regarding image properties, sizes are non-uniform, with 2 dominant aspect ratios, 500 by 333 and 333 by 500, indicating landscape and portrait orientations respectively. Color analysis shows a warm tone dataset with R larger than B, G larger than B channel means, and mean brightness of approximately 112 out of 255. For the text modality, captions average 11.8 words in length. Word frequency analysis shows dog, man, and two are the most frequent words after stop word removal, and the top bigrams are white dog, brown dog, and black dog. This points to a strong subject bias. The dataset is heavily skewed toward dogs and human subjects. Cross-model analysis using pairwise checkered similarity between captions for the same image gave a mean of approximately 0.28, indicating moderate but not strong inter-annotator agreement. This means the 5 captions per image describe the same scene but often focus on different details. Part of speech analysis shows nouns dominate the captions at 34.2% of all tokens, which is expected for descriptive image captions. Verbs account for 12% and adjectives around 10%. However, we also detected a gender bias. Male gender words appear at 1.42 times the frequency of female gender words. The most common male terms are man, boy, and he, while female terms women, girl, and she appear less frequently. This is an important bias to be aware of when training captioning or retrieval models. Let's consolidate the key findings from the flicker rate multimodal analysis before moving to the comparative summary. We confirm 44,002 multimodal pairs with essentially complete image text alignment. Captions average 12 words. 61% start with the article A, and nouns dominate the vocabulary, all typical of crowdsourced descriptive text. Subject bias is a real concern. Dogs, men, and women are heavily overrepresented as described subjects, meaning a model trained on this data will be disproportionately better at captioning those subjects than others. The checker similarity of 0.28 also tells us annotators had only moderate agreement, so the captions are diverse but not always consistent. Gender bias at a 1.42 male to female word ratio is another issue worth flagging for fairness-sensitive applications. And finally, non-uniform image sizes. Mean resizing is mandatory before any model training. For pre-processing, images should be resized to 222 by 222 to match standard vision backbone input sizes. Then normalized and augmented. Text captions should be lowercase, tokenized with BPE, and padded or truncated to a fixed length. At the cross-model level, any corrupted or duplicate pairs should be dropped, and the dataset's biases should be explicitly acknowledged. Given that 8,000 images is a relatively small collection for vision language tasks, we recommend pre-training on a larger dataset like COCO first, then fine-tuning on flicker rate. Here's a side-by-side comparison across all four modalities. In terms of size, image and text datasets are much larger and tabular. Missing values were essentially zero across all datasets, a clean collection overall. Class balance varies. Tabular was perfect. Image was moderately imbalanced at 3 times, and text and multimodal don't have a simple class balance concept. Key issues per modality. Tabular needs feature engineering. Text is characterized by very short answers. SVHN has noise from real-world photography plus class imbalance, and flicker rate has subject bias from its caption distribution. The 4 lessons we take away are: first, each modality demands its own specific EDA techniques. There's no one-size-fits-all approach. Second, visualization is essential. Many patterns like class imbalance and bias are only visible once you plot the data. Third, data quality assessment should always come before any analysis. And fourth, EDA findings directly drive pre-processing and model selection decision.